Please join me in welcoming to the Distinctive Voices podium, Dr. Mike Brown.
Thanks, Jennifer, and thanks everybody for coming. I think it's true that this is the first actual talk I've given in person post-pandemic. I've given like an infinite number of Zoom talks, and so if you guys could all just put like little boxes around yourselves, I'll be a little bit more comfortable. But so it's fun to actually be here and have a real audience. So feel free to do things like real audiences do, like throw things in catcall and all that stuff. I'll be much happier that way. So I'm going to tell you the story about our search and why we think there's a new planet out there and a search for a new planet. But to tell you the story, I want to take you back to the last time in human history that you could see all of the known planets. And this would have been something like 1780. In 1780, you could look up in the sky, and if you knew to look low, you could find Mercury close to the sun setting or rising. You could always find the very bright Venus, easy to find. Mars, easy to find, nice and red. Jupiter, you can't miss Jupiter. Saturn, even not so bad. And then that's it. Those were the known planets. You knew them all. And in 1780, I've looked at books written at that time if people speculated about the existence of new planets. And as far as I can tell, they didn't. It doesn't mean that people didn't talk about it, but no one wrote down, like, what if with these new telescopes we discovered, we looked out into space and found new planets out there. It's funny because people realized there were new stars that they hadn't seen until they got the telescopes. There were moons around things like Jupiter that they hadn't seen without the telescopes. Saturn had ears, which is kind of strange. But as far as I can tell, nobody thought about new planets. And so it was by accident, and a careful accident, that William Herschel in 1781, with his brand new super fancy telescope that was kind of the size of an entire house, took the crispest, I was about to say pictures, didn't take pictures. He could look through it and see the crispest images of the stars, just little pinpoints of light, and he was mapping where the stars were to try to understand the structure of what we now know of as the Milky Way galaxy. They didn't know what the Milky Way galaxy was. So he was mapping where the stars were in the sky, and he would look through his telescope and put it on the map, and look through the telescope and put it on his map. And he got to one spot in the sky, and there was something that didn't look like a little star. It was a fuzzball. And he could tell it was a fuzzball because he had that really good telescope. And it's okay, there are many fuzzballs out in the sky. There are things that we now know are galaxies and planetary nebulae and all these beautiful things you see pictures of. So he didn't immediately think anything of it, but what he did, because he was a very careful astronomer, he went back the next night and double-checked all of his positions of his stars, and he realized that the fuzzball had moved. As soon as you see it move, you realize it's not a star distant in our galaxy or any of these other galaxies or planetary nebulae. It's something in our solar system. It was something in our solar system, but it was moving so slowly that very quickly he realized it was beyond the orbit of Saturn. Even after having found this, he was resistant to the idea that he had just found a planet. There were other things that people knew went beyond the orbit of Saturn. There were comets. So comets were known at that point. They came in close to the sun, but they went out much further away and came back. So he thought maybe it's just a comet. Maybe it's, we'll have to watch its orbit and see if it's in a circular orbit around the sun. He was eventually convinced to start to call it a planet. He needed a name for it. He tried to call it George. That didn't stick for very long. This is actually a true story. But it was still not clear that it was really a planet because it was not clear what its orbit was. It had just been discovered. We now know that Uranus takes 84 years to go around the sun. So you kind of want to see a significant part of that orbit before you really understand what the orbit is. And so that's, decades that you have to watch it, maybe even 80 years you have to watch it. So astronomers dutifully watched its position for many years. And then an astronomer, the astronomer at the observatory in Paris, had a very clever idea, and he wrote this fascinating sounding book, Astronomical Tables of Jupiter, Saturn, and Uranus, and it really is as good as it sounds. His titles are the best, though. I gotta work on better titles. He's got all the good ones there. In this book, he cataloged the positions of Jupiter and Saturn and Uranus, but more importantly, he was what we would call today a theoretical astrophysicist. He was trying to understand the theory of where they were supposed to be in the sky. At this point, gravity was understood well enough, and we know that things move in elliptical orbits around the sun, but they don't actually move in perfectly elliptical orbits around the sun because the gravitational pull of each planet influences the other planets, and so it modifies them just a little bit. So you can, if you work out the mathematics, you can predict where the planets are supposed to be, and he did. And here's math. There's an error, literally true. One of these numbers in here, somebody figured out is wrong, but it wasn't too wrong, so it was still worked out more or less okay. This is actually his theory of where Uranus should be. So Uranus's position based on his observations and based on perturbations due to Jupiter and Saturn. And he was comparing his observations to the positions of Uranus, and I'm going to zoom in on this table here because this is a fascinating table. I'm not zooming in on this table. In my other presentation, I would zoom in on this table, and instead I'm going to make you stare at this very carefully. Here is 1781 when it was discovered, but the amazing thing is there's data going all the way back to 1690. Nearly 100 years before Herschel discovered Uranus was the first time Uranus was actually seen. And it was seen because an astronomer, Flamsteed, was cataloging positions of stars, and he found one star in the constellation Taurus. It was the 33rd brightest star in the constellation of Taurus, so it has the very exciting name 33 Tauri, and he just cataloged where it was and moved on. Went the next day, he looked somewhere else, and it turns out it was Uranus. How did Bouvard figure it out? Well, he took his own observations and the 20 years of observations after that and started leapfrogging back and found, he said, look, somebody was looking at stars in this area in 1771 and in 1753 and in 1690, and he went back and found each one and realized that that star that they cataloged was no longer there. So in all of the Flamsteed famous catalogs and these numbers that we still use today, you can go off to a telescope and look at 32 Tauri, and you can look at 34 Tauri, and there is no 33 Tauri. They never went and renumbered it. It's the only missing number, and it was because it was discovered in 1690. But the important thing about this table is the next number. This next number is the difference between these predictions, Bouvard's predictions, and where the astronomer said that Uranus was. And there's pluses and there's minuses. You don't have to worry about the numbers too much. But you see, sometimes it's a little in front for a long time, behind for a long time, back to being in front for a long time. As I said before, Bouvard was the preeminent theoretical astrophysicist of the day, and I have to say, I know many people who would consider themselves the preeminent astrophysicists of today, and they're all exactly the same. Bouvard, you can actually read it right here. Bouvard basically said, my theory is perfect, the astronomers are wrong, they need to make better observations. And so the astronomers very admonished, like, oh, I'm sorry, I'll go do better. So they went and spent, so this went all the way up to 1819. They spent the next 20 years making as precise measurements of the position of Uranus as possible. And it was still in the wrong place. So Bouvard's got it out. He does say that there's an alternative possibility down here, which is that maybe there's something beyond the orbit of Uranus that's tugging it a little bit faster sometimes, pulling it a little bit back sometimes. And by about 1840, this was widely accepted. Everybody who was paying attention to the outer solar system pretty much agreed that there must be another planet out there. And the only question was how to find it. This problem was finally solved by another French astronomer at the same observatory as Bouvard, and actually using these very data from Bouvard, Urbain Le Verrier, he figured out the mathematics of how to convert these numbers into a prediction of where this planet-tugging Uranus should be. He sent his predictions by telegram to the observatory in Berlin, and they opened up the telescope that very first night, and there it was, like literally right there in the very first night. It's to me, I still kind of get goosebumps when I think about it. It is kind of one of the most amazing stories of this prediction, and then discrepancy, and then a new prediction, and then confirmation. That's just like the what we think of science is supposed to be like. And I also feel like this was in 1846, that this is a point where people understood gravity. People knew, like, if you dropped things, you could calculate how long it took. I'm not going to drop your laser pointer, I promise. How long it's going to take to get to the bottom. But I don't think people really believed you could use that fancy physics, math stuff to predict a planet. That's just like a little bit too much. But at this point, it was suddenly clear that you could do this. It was so clear that you could do this that everybody wanted to get on the act. So Leverrier became extremely famous for having, as the phrase went, discovered a planet at the tip of his pencil, with the tip of his pencil, one of the two. He has a statue in Paris at the observatory looking up, I forget what boulevard it is, but straight up to Notre Dame. His name was one of the only 50 people originally inscribed in the Eiffel Tower. Mine's there now, but it wasn't there originally. It's not supposed to be, though. So, I mean, it was very famous, and other astronomers looked up and like, I want to do that. I want to be that famous. So they started predicting planets basically left and right. Within a year, there was at least one set of new planets predicted, which basically said, yeah, Uranus is here and Neptune is great, but it's still not enough. There needs to be something else a little bit past Neptune to explain the perturbations. It's not good enough. And then another astronomer said the same thing, and then there were other planets. So we actually counted up recently, and we found, I think, something like 35 individual predictions of a new planet from some astronomer somewhere between the discovery of Neptune and now. And of those 35, they're always wrong. They're always wrong, and sometimes they're a little bit crazy and wrong. Sometimes they're just wrong because they're wrong. But they're always wrong, and you never look good predicting planets because people just kind of think you're crazy. The one that seemed right at first, but turned out to be wrong, was, of course, the most famous of these planetary predictions was Percival Lowell. Percival Lowell was an American astronomer from Boston, and for very crazy reasons that if anybody asks me about, I will tell you the crazy reasons why. But for very crazy reasons, he wanted to predict the location of a new planet. He was convinced there was one out there. And so he made predictions. He actually sent a team of astronomers up to the top of Mount Wilson. This is before Mount Wilson had the big telescopes up there, but it was still considered a great place to do astronomy. So he sent a team of astronomers up there to take a picture of the sky where he predicted his planet should be. And there it is. Did you guys see it? Yeah, he didn't see it either. So he was convinced that this thing that was perturbing Uranus and Neptune had to be pretty big, possibly even as massive as Jupiter to explain the observations. And that would have made it kind of like this big. And there's nothing kind of that big in the sky, in this area of the sky. So he was disappointed. He went back to the drawing board, kept on his predictions, and he passed away before anything was found. But before he passed away, he founded the Lowell Observatory in Flagstaff. I'm sure somebody here has been there. Lowell, yes? There we go. I knew somebody would. It's a cool place to visit if you're ever out there. He founded the observatory in Flagstaff. One of the reasons was to look for this planet. And he hired Clyde Tombaugh off the farm in Illinois to look for this planet. And Clyde Tombaugh started taking pictures of the sky, photographic plates, and he realized, he was smart enough to realize he didn't know what a planet was going to look like. But he realized, just like Herschel did back in 1781, if you take a picture of the sky one night and you take a picture of the sky the next night, it moves. Did you guys see it move? You want to try again? Okay, here we go. Here's the first night. Second night. Who thinks they saw it? Nah, you didn't. Let's try again. First night? Yeah, maybe? Second night? Maybe? Okay, I don't know why, but I'm not a physiologist, but apparently if you repeat things 4 times, people always see it the 4th time. So we'll try this the 4th time. Here's one night. Here is the second night. Did anybody actually see the right ones? Yeah, I still miss them every time I see it. These are the actual discovery images of Pluto from Clyde Tombaugh from 1930. Finding this was an amazing job because these days we do everything by computer. He actually looked through all the stuff by eye, and so it was just amazing. Amazing discovery, front page of the New York Times. 9th planet discovered on the edge of the solar system, first found in 84 years, far beyond Neptune. This is all correct. Sighted January 21st, still true. Seen in Flagstaff, also true. Special photo telescope, I don't know what that means, but it's probably true. So far, so good. The headlines get a little bit smaller. Astronomers hail finding, I think they did. The sphere possibly larger than Jupiter. And 4 billion miles away, that part's true. So possibly larger than Jupiter, it's this really interesting part of the story. So first off, it's wrong. And it is wrong by a factor of 250,000. So it's not even for an astronomer, it's not a small discrepancy. Like factors of 100, we can sort of sweep under the rug. 250,000 is getting on there. But it's an interesting thing. And to me, this is an interesting story about science, the way science can sometimes get off the rails a little bit, but the way science also gets back on the rails by doing more science. So it got off the rails. People were looking for a massive planet out there. They found something, therefore it had to be the thing they were looking for. Couldn't have just been a coincidence that some little thing was out there at the same time. It turns out it was just a coincidence. Pluto is so tiny that there's no perturbation to Uranus and Neptune at all. But that was 1930, and so Pluto was this planet in 1930 primarily because people thought it was possibly larger than, not just as large as Jupiter, possibly larger than Jupiter, which is a little crazy. So I'll remind you where it is. I don't remember which one it is now. I don't even know. See, I can find it in the second one. It's that one, right? Oh, there it is. Okay, it's there, and then it's there. Yeah, okay. So, possibly larger than Jupiter. It should have been something like this big. There was something funny going on, and people kind of didn't really want to think about it too much. Although I did read a fascinating paper that said the reason it's not that it's larger than Jupiter, it's just as massive as Jupiter, which is why it still perturbs things. And the reason it's as massive as Jupiter is because it's made entirely of uranium. This was 1930. They didn't realize just what a bad idea that would be at this point. But it would be a really bad idea. So turns out the reason it looks so small is not because of any kind of weird effects. It looks so small because it's really small. In this whole debate about Pluto, is it a planet, not a planet, blah, 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 one of the things that was lost to a lot of people is just how small it really is. I mean, when you see pictures of the solar system, you often see these things like my daughter had these all the time, like a lunchbox with the planets on it, always with Pluto, because my friends loved to give her lunchboxes with Pluto on them. And they would always be like, Jupiter is the biggest, Saturn's a little smaller, and the Earth is clearly smaller than Jupiter, but they're all kind of the same size because it looks better on your lunchbox, and they can all have faces on them and stuff. And if you had a real lunchbox, your real lunchbox, I'm gonna copyright this and go sell lunchboxes. It should look like this. Here's what the scale of the actual planets, which very few people really know. Here's Jupiter, huge in the background, so big it doesn't fit. Saturn, without its rings, is really quite large still. Uranus and Neptune, terrestrial planets, Mercury, Venus, Earth, and Mars. And even here are the asteroids between Mars and Jupiter, and these are the 10 largest. This is Ceres, that there was a spacecraft was in orbit around it for a while. And these are there are 10 of them that are big enough to be 1 PowerPoint pixel. That was my criterion for including them. There are many other ones in there too. Where's Pluto? Don't blink. There it is. It's that little thing way down there. It's not what you would think of if you were to sort of continue the pattern of what the next planet should be. It doesn't look like that, and it is really tiny. You know, but there was nothing else there in 1930 and for 60 years, and so it was called a planet, and it stayed a planet. The other thing that was weird about Pluto, I'll remind you, is here are the orbits now. These are the terrestrial planets: Jupiter, Saturn, Uranus, Neptune. The orbit of Pluto was always weird. It goes inside the orbit of Neptune for a little bit. It comes all the way out here. It's much more eccentric. These are mostly circular. Pluto is on this very eccentric orbit. And even stranger is that this eccentric orbit is tilted compared to the planets here. It's tilted by about 20 degrees. Very strange. It didn't make any sense, but it was, there was nothing else there. It was just this oddball at the edge of the solar system, and nobody knew what to call it except for calling it a planet. That all changed in 1992. In 1992, the first new object since Pluto was discovered beyond Neptune. And as of today, there are something like 4,000 objects known with orbits outside the orbit of Neptune. And if you look at those objects and you look at the orbits of those objects, they resemble the orbit of Pluto in many ways. One is they're tilted in all random directions. They're not just stuck in the plane here. And if you now tilt it back on its front, you'll see that just like Pluto, some of them go inside the orbit of Neptune. They're eccentric. Some of them don't. Some of them stay outside of Neptune this whole time. Some of them are on some of them go way inside here before they're coming back out. It's really this whole hodgepodge of objects out here in this region that we now call the Kuiper Belt, which is kind of like an icy version of the asteroid belt that exists between Mars and Jupiter. So even back in 2002, when we were still mistakenly calling Pluto a planet, it was becoming really clear that Pluto was part of this population and really didn't belong with these other ones. And the real kicker, I would say, was to put the new objects on this plot down here. There's Pluto. There's one that's exactly the same size within like 100 kilometers. That's Eris. Eris is the one that we found that was basically the nail in the coffin of Pluto as a planet, which was fun. But then there's all these other ones that are nearly the same size. So it really is, this population out there is quite extensive. One of the things we learned by looking at all these objects out there is that they all make sense. Their orbits make sense. The idea that there was a giant planet perturbing Uranus and Neptune was wrong. It was wrong for a very specific reason. It was wrong because it was looking at observations of where Uranus and Neptune were and saying that those observations didn't make sense. And it was because Bouvard was right. Astronomers needed to make better observations, and his theory actually was pretty good. And his modified theory was pretty good, explained everything. So as of about 2002, the entire solar system makes sense. There are 8 planets. There are a bunch of objects in the Kuiper Belt. Everything is merrily going around, and we understand everything. It's always bad when you understand everything because something's going to come along to ruin it, or it's great when something comes along to ruin it. In 2003, we discovered this new object that kind of ruined everything in a fabulous way. And it's got an orbit that's so crazy it doesn't fit on the screen, so I have to put it over here. Sedna, it has an incredibly eccentric orbit. It takes 10,000 years to go around the sun. And that's all weird enough to begin with. But the really weird thing about Sedna is if you notice how far from Neptune it always stays. It never comes close to any planet. And that's weird for a specific reason. And the reason is because we think that all of these objects, including all the planets, form in a disk around the sun. And when they form in very circular orbits. The way you get into a not circular orbit, like all the objects in the Kuiper Belt, is you get perturbed by a planet. You get too close to a planet gives you a kick. you get that kick and your orbit is modified. You can't get a kick if you never get close to a planet. So in 2003, we knew something was up. There had to be something else in our solar system that had given Sedna a kick. We thought we knew the answer, and we thought the answer was that it must have happened 4.5 billion years ago as the sun was born, and there were other stars nearby also being born. The sun was probably born in a cluster of stars, and those stars would have perturbed the orbit of Sedna. And I was very excited because if that was true, you could go find more objects like this, and you could start to sort of read this fossil record of the sun's birth, which is a pretty cool thing. As you'll see, that's all wrong, but it was a cool idea at the time. So we spent 10 years looking for things like Sedna to try to read this fossil record. And what we found instead was something that confused us at first. And here's what we found. We found, even after 10 years, these are the most distant objects that we know of in the solar system. So they're faint, they're hard to find. We don't find a lot of them. And at this point, there's 1, 2, 3, 4, 5, 6, 7 of them. 1, 2, I think there's 6. 6 of them. This purple one is, they're all purple, but this purpler one is Sedna. And they all have orbits kind of like Sedna, but they all have one thing in common, which is pretty obvious when you just look at this plot, is that they're all pulled off in this direction. That's weird. There's no particular reason things should all be pulled off in one direction. Even if a star had come by 4.5 billion years ago and pulled them off in this direction, the orbits in our solar system change over time, and one of the ways they change is they precess. That precession, just basically think of it like the direction that these things point is all like hands of a clock, and they all move the hands of the clock, and they all move at slightly different rates. And so even if they were lined up 4.5 billion years ago, they'd be totally random right now. So there's no reason they should be lined up like this. So at this point, I walked down the hallway to my colleague, Konstantin Batygin, and I'm like, Konstantin, why are they doing this? This doesn't make sense. And he looked at me and he said, maybe it's a planet out there. And we both laughed, because that's dumb. And we know there's not another planet out there because everybody who predicts that there's a planet out there is wrong. And we certainly were not going to be the 36th and 37th astronomers to predict a planet and be wrong. So we spent 2 years trying to work out what possibly could cause this. It's not a planet, because it can't be a planet, because that's dumb. And we thought about the gravity of these objects all collectively. We thought about the full Milky Way galaxy doing something. We looked for other subtle effects that could do it, and we could not find anything. And we felt kind of like failures, and so we were like, well, we could look to see if a planet works. And we're like, oh no. So we started doing out the math. I say we, Konstantin does the math. I do the telescopes. He did math. He probably did it right. And he's like, a planet works really well. And the way it works is you have all these objects here, and you have like a big planet on an orbit like this that kind of hugs these, and they stay inside there forever. And I'm like, yeah, okay, we can think about it. So we ran some computer simulations, and I want to show you how the computer simulations look, because it's kind of cool to watch. So here's what we're going to see. This little circle right there, that's the orbit of Neptune. So we are way zoomed out in the solar system. This solid line you'll see more of as time goes on. This is the orbit of a planet, a giant planet in the outer part of the solar system. And each of these blue things is a test particle. We put those eccentric objects on orbits in the outer solar system, and we watch them move. You're not going to see the things moving around their orbits. You're just going to see the drawings of their orbits, and you're going to watch the orbits move with time. So let's go. So the first thing you notice is a lot of the stuff disappears really quickly. And it disappears really quickly because crossing the orbit of a giant planet is a really bad idea. You're going to come close to it. You're going to get ejected from the solar system. Every time you see one of these disappear, it's because it gets ejected from the solar system. The next thing you see is that these things that I've now colored green on the inside, they're kind of just hanging out, minding their own business. They are precessing. That's that changing of the direction of the orbit that you see. So if you're close enough in, You don't really cross the orbit of the planet, you just precess. If you cross the orbit of the planet, it's bad news, but in here you can be saved. So let's find one that gets saved. Here's one that's, no, that doesn't stay. This guy stays. No, it doesn't stay. Okay. All right, this one, no. This one, no. This one, no. This one does, though. No, this one really, no. Go, stay. So the bad news is none of them stay. None of them stay over here. They stay over here. And we looked at this and we were like, what did we do? Did we calculate it wrong? What? And we realized we had made one very simple assumption in our original calculations, which was we were ignoring orbits that cross giant planets because that's bad. Of course, that means we were ignoring all these. But when we saw this, we realized, we slapped our foreheads and realized this is what makes sense. The only objects that last are objects that stay as far away from this planet as possible. And by that I mean, these things, when they go in orbits, a planet spends most of its time in the distant part, and then it comes in here and it goes fast through here, slow, fast. And these do too, slow, fast. They do that, which means they come screaming through this part of the solar system, as this is too. So they may interact, but they go quickly. So they're trying to avoid each other as much as possible. Instead, if the objects had been over here, the planet spends all its time out here, the object spends all its time out here, they're too close to each other, they would eventually get ejected. I'm going to take questions at the end, if that's okay.
What slide number is that?
I have no idea. I don't have slide numbers on here, so I can't tell you. All right, so what does this mean? This means that when we see these objects like this, which we thought meant that there was a planet like that, really means that we should have thought of the objects over here and the planet like that. And we got this result, and we thought, this is really fun, but come on. It's easy to come up with an explanation of what we're seeing. Astronomers can explain anything, and then if you tell them, oh, I'm sorry, I flipped it, I meant you were supposed to explain this, they're like, oh, I have an even better explanation for that. What you really want in science is to have a prediction and have that prediction come true. So the obvious prediction is we'll find more things on orbits like this and not very many on orbits like this. There should be a couple. But that's a slow one. Remember, it took 10 years to find these, and so we didn't want to wait 10 years. We realized there was one other prediction that was a little worrisome, which was, in addition to these things, there's another set of things. I'm not showing them on the slide here, but occasionally one of these objects gets a little bit too close to Neptune, and when that happens, its orbit tilts down like this, but it also, instead of being in the plane of the solar system, it tilts by 90 degrees this way. So now it's on an orbit like this, and it goes straight down and straight back up, and they also go this way too. Kind of looks like wings when you look at it. And we didn't know of any. And we went and looked through a bunch of different catalogs and didn't find any, and it was enough that we were about ready to throw away our theory because we couldn't find this. And then I forgot that there was this one catalog I hadn't looked at for kind of silly reasons, and I went and looked and I realized, oh, there are all these objects that are going straight up and down through the solar system. Called Konstantin in my office, and we took this plot and put them on there, and it was perfect. They were exactly where they were supposed to be. And this was the moment where I think both of our jaws dropped, and we're like, oh, there's actually a planet out there. So since then, we have found more of these objects. Here's the next 8 years worth of things that we found, mostly off in this direction. One in the wrong direction, which is good. Again, they should at least be about 10% should be in the wrong direction. We were getting worried until this one was found. So the theory is very good at explaining these things we see. We keep on coming up with other tests because we still, like, if we're going to be wrong, we want to prove ourselves wrong before somebody else does. So actually, Konstantin just came up with a really good one back in January that's about how this planet pushes the orbits inside the orbit of Neptune sometimes in a way that doesn't happen if there's not, and we looked at all the orbits inside Neptune and it fits perfectly again. So I think it is fair to say that it is very, very difficult to explain the solar system without having a planet out there. You know, there are about 6 different things that the planet that predicts. All of them come true, and if there's no planet, you have to come up with 6 new explanations, of which there are none. So there's a planet out there. So what kind of planet is it out there? Well, one of the things we do is we do thousands of those computer simulations like you just saw, and in those thousands of computer simulations, we vary all the parameters. We make the planet a little more massive, a little less massive, a little more elongated, a little tilted, a little less tilted, and we can learn some things about it. One of the things we learn is how big it is. So in our very early paper, we thought it was somewhere between 5 and 20 times the mass of the Earth. Now we're a little better now. We'll say 7. 7 times the mass of the Earth is a super interesting mass. And the reason is because it is between the mass of Uranus, which is about 14.5 times the mass of the Earth, and the mass of the Earth, which is precisely 1 times the mass of the Earth. And we didn't know of any planets in our solar system in that range. And yet, if you look at stars in our galaxy, that's the most common mass of a planet there is out there. So I used to teach this class when I talked about planets around other stars, and I'd say, isn't it weird? You know, the most common kind of planet is something like 5 to 10 Earth masses. We don't have one. I wonder why not. And the answer is we do. It's just really far away and going to be hard to find. So 7 times the mass of the Earth, which is really interesting. And it's really interesting because this means this is not a, like, let's all argue about it's slightly larger than Pluto and we'll argue about whether it's a planet or not. This is the 5th largest planet in our solar system. Here's our favorite slide again, and there it is. It's huge. It's huge. So the obvious question is, why haven't we found it? The answer is because it's really far away. It's probably something like 20 times further away than Neptune on this orbit that it has. So just like we did all those computer simulations to figure out how big it is, we did all those computer simulations to figure out what its orbit was, where in the sky it is, and I'm going to show you this one. This is one of the figures from our paper, but I think it's easy enough to figure out what's going on. This is a map of the sky and our prediction of where it should be. And where it's red is it's most likely, where it's blue, it's not going to be at all. Where it's light blue, it's less likely. So our most likely region is right in here. And this is the celestial equator, straight across the equator here. This black line is the plane of the solar system, the ecliptic, where all the planets are. And this region is the Milky Way galaxy. So Milky Way galaxy, it might well be in the middle of the Milky Way galaxy, which is painful because that means we have to sort through all the stars in the Milky Way galaxy to find it too. So how far away is it? Well, in these different regions, in the region where we think it really is, it's going to be something like 400 AU. And AU is a distance from the Earth to the Sun. 400 AU is about 15 times the distance to Neptune. So Neptune would be somewhere down here. So it's really, really far away. And it's really ranges from, this is how bright it is. It's in these crazy units that astronomers use called magnitudes. But for most of you who don't think about it, I will put the real scale over here, which is down in here, it's bright enough to see in backyard telescopes. If it were at its closest and sort of its biggest, you could see it. Somebody around here has a backyard telescope that can see things that are 18th magnitude. Anybody? Anybody? There you go. See? Somebody. So if it's here, we'll all come to your house and we'll come check it out. But you have to be in the southern hemisphere because that's where it comes closest, and so we'll have to move your telescope. So probably not backyard telescopes. Up here, it's kind of like 100 modest-sized telescopes you could probably use. If it's up here, it's some of the largest telescopes on the planet, and if it's here, it's just a few of the really, really largest telescopes. And if it's up here, super duper tough. I hope it's not up here. We have systematically over the past now 8 years been, the way we do this is we start looking for the easy things. Look to see if it's bright. So we take the small telescopes. Small telescopes are great because you can get a lot of time on the sky on a small telescope because not as many people want to use them, so you can spend a lot of time. So we've really kind of covered the entire sky to about this level. Then we go off to some of the big telescopes. The big one that we like to use is the Subaru telescope. It's the Japanese national telescope on the summit of Mauna Kea in Hawaii. And that's, we're only doing this little patch right through here. And I just literally finished analyzing the data this morning. We did not find it. I was hoping to be able to say, and here it is. And that covers this. And what that means is it's going to be in this tough region. And it's also going to be in this region in the middle of the Milky Way galaxy. It's going to be a difficult object to find. I have high hopes for this new telescope that's coming online in a year. What is this, 2024? It's a year from now, 2 years from now. The Vera Rubin Observatory, LSST down in Chile, is basically a large telescope, sort of this size, that basically covers the whole sky every 3 days and looks for anything that's out there moving. This should find it. If it's anywhere except for right up in here, this shall find it, and it'll rule out everything, and then we'll really go and beat this part in here. So I just want to end with a thought about where it really is in the sky, and a thought about that it really is in the sky. It sometimes can feel very abstract sitting around doing the computer simulations and analyzing data, trying to link orbits and everything else. But what I like to do is I like to go up in the sky, when I go outside, particularly like a night, if it's still as clear as it was at sunset, it's going to be beautiful when you walk out these doors. And when you walk out these doors, I want everybody to do this. I want you to look up and I want you to find everybody's favorite constellation. Is there anyone this is not their favorite constellation? No. The answer is no. Orion is the best constellation. And you know, Orion in Greek mythology is fighting. Here's Taurus, the bull over here. The horns are right here. And Orion, this is either a bow that he's shooting or it's a shield that he's protecting himself from this Taurus. And this is this cosmic battleground. And the orbit of Planet 9 goes right through the middle of this cosmic battleground right here. I think that when we find it, I think it's going to be just a little bit above Orion's head. And as you can see, look at how many more stars there are right here than there are right out in here. This is because this is the Milky Way galaxy. When we're looking for it, we have to basically get rid of every star in the sky looking for the things that move. So this is the painful work that we still have ahead of us. But I think we're there. I think we're going to find it. I am exceedingly confident that it's really there, and I'm pretty sure it's going to be right up in this area. And I want you just to go look at Orion's head and just think about it for a minute. It's really there. This is not just, haha, that was a good talk, all fun. But it's really, there's a planet out there, and in the next couple of years, somebody will find it and announce that it's there. And I just want to finally end, the final end. This is the poster we had at the beginning. This is our poster that we ripped off fair and square from, of course, movie Plan 9 from Outer Space. Has anyone actually seen the movie Plan 9 from Outer Space? Really? Like, actually watch the whole thing? Wow. Okay, so it's famous. Does anybody know what it's most famous for? Well, so it is actually, Bela Lugosi is in it. It was posthumously in it. He was like spliced into it after he had already passed away. But it's most famous, I think, because it was actually voted, this part's literally true, the worst movie ever made. You can go look it up on Wikipedia. This is all really true. And I mean, it's terrible. This is why I'm like, did you actually? Because there's Bela Lugosi, there's Vampira, there's Konstantin is actually in it right there. And it was directed by Ed Wood, who also directed good movies, and so it's kind of weird. But Ed Wood was a genius, and one way he was a genius, this is 1959, right? So think about it. Pluto had been discovered like 29 years earlier. It was not going to be demoted for another 50 years. Here's the cemetery scene. They're digging up space zombies, I think. But look, I'm going to zoom in on this part, and Ed Wood, genius, 1959, already figured it out. R.I.P. Pluto, right there. It's already gone. Okay, so I'm happy to take questions, and thanks for being here.
Thanks.